Is my screen visible?
Yeah.
Yeah, it's visible.
Yeah, so this is something that we'll be wanting to prove by the end of this class. So it's called the Erdos-Szekeres theorem. So it states that there exists a minimal number ES of n such that if there are capital N greater than or equal to ES of n points in the plane, no three collinear, then there exists n points which form a convex n-gon. Is the statement clear?
Yeah.
So we won't prove it now. We'll first do surprisingly Ramsey theory. And sorry for the handwriting. So what is Ramsey theory? Oh, we'll start with an example. So we have six people, and knowing is mutual. Knowing is mutual. What does this mean? Is that if A knows B, then B knows A. And if A does not know B, then B does not know A. So we need to prove that there exists three of them who know each other, or there exists three of them who don't know each other. So we have six people, and knowing is a mutual relationship. That is, if A knows B, then B knows A. And if A does not know B, then B does not know A. And we need to prove that there exist three of them, such that each of them know the other two, or there exist three of them who don't know each other. This is clearly non-trivial. So how do we go about proving this? So we represent the six people by six vertices of a graph. And what do we want to prove is that we have three people A, B, C, and each of them know the other two. And we will depict knowing by a red edge and not knowing by a blue edge. Not by a blue edge. We can do it. We can just say it with edges because we are assuming that knowing is a mutual relationship. So we don't need to go to directed edges. So what do you want to prove is that there are three people, is that each of them know the other two. That is, A knows both B and C, B knows both A and C, and C knows both A and B. So we either want to prove a red triangle, or we want three people A, B, C. None of them know the other two. That is, A does not know B, A does not know C, and B does not know C. So in these six vertices, when we're coloring each edge by red or blue edge, so we need to find a red triangle or a blue triangle. So to prove this, let's take any vertex to this guy. It is connected by the remaining five vertices by some edge, a red or blue. So by PHP, there would exist either at least three red edges or at least three blue edges. So assume that we have at least three red edges. So let these three red edges be the three edges we want. And let the remaining vertices, these three green vertices. And so if any edge is red in these green three vertices, then we clearly have a red triangle, which is what we wanted. So if any of these edges in this green set of vertices is red, then we have a red triangle. So the only case that remains is when all these vertices, all these edges are blue. Sorry. All these edges are blue. But then we clearly have a blue triangle. So in either case, we have either a red triangle or a blue triangle, which completes our proof. So is the proof clear?
Yes.
Okay, cool. So also that is bound 6 is sharp. That is, if you have five vertices and we color the edges of this K5 complete graph with 5 vertices, red or blue, then we can have such a coloring in which there is no red triangle, neither a blue triangle. An example is this. Clearly, there is no red triangle or blue triangle. So we say that R of 3 comma 3 is equal to 6. So what does this mean? I'll just write the definition. There exists a minimal number R of R comma B such that if capital N is at least R of R comma B and we color the edges of a Kn, we color it red or blue, then there exists a Kr with red edges or a Kb with blue edges. So the statement says that there exists a minimal number R of R comma B such that if capital N is at least R of R comma B and we color the edges of a Kn red or blue, then there exists a Kr with red edges or a Kb with blue edges. So is the statement clear?
Yeah.
And so why does R of 3 comma 3 is equal to 6?
Kn means n.
Sorry, can you repeat?
Does Kn means endpoints?
A Kn means a complete graph with n vertices.
Okay.
Like a K6 was this way we're coloring each edge red or blue. Okay, cool. So and why is R of 3 comma 3 6? Just because if you have at least 6 vertices and we're coloring the edges of a Kn with red or blue, then we have a K3, which is a triangle. We have a triangle with red edges or a triangle with blue edges, which is what we showed above. That is, if you have at least 6 vertices, then we have a red triangle or a blue triangle. And why 6 the minimal number? Because we showed that a construction for 5 that there is no red triangle or blue triangle. And thus R comma 3 comma 3 is 6. And so the existence of arc of R comma B is not trivial. So we'll prove it. Oh, and also that R and B have to be at least 2. This series is not working.
Also, we are going to prove its existence.
Sorry. Just
So we are going to prove its existence.
yes, we are going to prove that R of R comma B exists. This is not working. Oh my god. Why? Oh my god.
So R of R comma B is like the number of red triangles and blue triangles.
No, R of R comma B is just a number which you want to prove exists. Such that if you have a capital N, if you have at least R of R comma B points in the plane, sorry, I should say R of R comma B vertices, and we color the edges of a Kn red or blue, then there is a Kr. Kr is a complete graph with R vertices with red edges or a Kb with blue edges. I'm sorry, this is just not working. Yay. I'm supposed to delete this thing. Delete, 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 delete. Ah, oh my god. I'm sorry. Delete. Yay.
It's okay. You can take your time.
You can do it. You can take your time to.
Okay, perfect. Yes, what I was saying that we need to assume that R and B have to be at least 2. Just because a K1 with an edge makes no sense. So how do we prove that R of R, comma B exists? We'll induct an R plus B. For the base case, we
Basically,
can.
the base case is the hexagon, like the 6 point graph.
Yes, yes, exactly.
Okay.
We can also take it 6, but we can also take it 5, but I'll just take it 6. Is exactly what you said, that R of 3, comma 3 would be 6, what we proved above. But there's just one more configuration, which is R of 4, comma 2. So what would R of 4, comma 2 be?
Oh, sorry, a 5 point graph.
Can you repeat? I don't know. Can you repeat? Hello, am I audible?
Yeah, audible.
Yes, so somebody was just asking something. Okay. So what can be the value of R of 4, comma 2? 2? Are you sure?
4 works, I think, right?
Yes, it does. So why?
Because if you have, let's say, less than 4, just take everything as uh, the left one is red, right? Okay, so take everything red.
Hmm.
You have a K3 with red edges. There is no K2 with blue, and this is not even a K4.
Yes.
Now take four vertices.
Just a sec. Yes.
If you have any two as blue, it will be a K2 with blue. So all
Yeah.
should be red, but in that case, you have a K4 with red.
Yeah. Perfect. So is everyone clear with that proof?
Yeah.
Okay, perfect. So we're done with the base case. And just because, like, as we did R of 4, comma 2 is 4, we can also prove that R of R, comma 2 is R by the exact same method. That is, if we have less R minus 1 vertices or at most R minus 1 vertices, we color all edges red. Color all edges red. And for a KR, if there exists a blue edge, then we are done. If there exists a blue edge, then done. So if all edges are red, all edges are red, then again we're done. Just because we have a KR with red edges. So by the induction hypothesis, we can assume that R of x comma y exists when x plus y is R plus b minus 1 and x and y are at least 2. And in particular, we need that R of R minus 1 comma B and R of R comma B minus 1 exist. This is the reason we got rid of the R of R comma 2 cases first, because otherwise you would have something like R of R comma 1, which we didn't define. So now we know that R of R minus 1 comma B and R of R comma B minus 1 both exist. Now with this we can prove that R of R comma B exists. And how do we do that? We show that R of R minus 1 comma B plus R of R comma B minus 1 vertices suffice. That is, if you have at least R of R minus 1 comma B plus R of R comma B minus 1 vertices, then we would have a red KR or a blue KR. Note that this does not mean that R of R comma B is R of R minus 1 comma B plus R of R comma B minus 1. This only means that R of R minus 1 comma B plus R of R comma B minus 1 is at least R of R comma B. If we prove that R of R minus 1 comma B plus R of R comma B minus 1 vertices suffice. Again, this does not mean that the equality holds right here. And to prove that these number of vertices suffice, we take any vertex V, and so it has loads of edges. So the number of edges of V is R of R minus 1 comma B plus R of R comma B minus 1 minus 1. Just because V is one vertex and the remaining vertices are these many. And we claim V has at least R of R minus 1 comma B red edges, or V has at least R of R comma B minus 1 blue edges. So we claim that V has at least R of R minus 1 comma B red edges or R of R comma B minus 1 blue edges. So if not, like if the claim is not true, then we must have at most R of R minus 1 comma B minus 1 red edges, and this is and we must have at most R of R comma B minus 1 blue edges. So if the claim is not true, then we must have that V has at most R of R minus 1 comma B minus 1 red edges and at most R of R comma B minus 1 blue edges. So total edges of V must be at most R of R minus 1 comma B minus 1 plus R of R comma B minus 1 minus 1, because the only choices of edges of V are red or blue, and we've showed that there is at most these many red edges and these many blue edges, and thus total edges of V must be the sum of these two. But we also showed that the total edges of V is R of R minus 1 comma B plus R of R comma B minus 1 minus 1. So this inequality is a contradiction. And thus V has at least R of R minus 1 comma B red edges or R of R comma B minus 1 blue edges. So is everything now okay? Any questions? Okay, assuming that is no questions. So if you take the first case, that is we have V and we have R of R minus 1 comma B red edges. That is the first case if V has at least R of R minus 1 comma B red edges. Then just because of we assume that R of R minus 1 comma B exists, so this red set of vertices to which V is connected by red edge, this has either kr minus 1 with red edges, or kb with blue edges. So yes, any questions?
Do you do this on PHP?
Sorry, your voice is quite low. Hello? Hello, can you repeat? Oh, we just proved it. Like we just claimed that. Yes, you can also use PHP, but we claim that V has at least R of R minus 1 comma B red edges or R of R comma B minus 1 blue edges. So is the proof of the claim clear? Okay, perfect. Like if not, then we clearly have a contradiction. You can just see the proof. Okay. So if V has at least R of R minus 1 comma B red edges, then this red set has either a KR minus 1 with red edges or a KB with blue edges. So if it has a KB with blue edges, then we are done. If it has a KR minus 1 with red edges, we just add V to these R minus 1 vertices. Why does this work? Because every edge in this KR minus 1 is already red, and as all edges in this red set were red, because every edge in this red set was red in V, like Vx is red, they call this set A. So for all x in A, edge Vx is red. And thus V is red to these all R minus 1 vertices, and we have a KR with red edges. And so for the other case, it is similar. I'll just do it for completeness. That is, if V and R of R comma B minus 1 blue edges. So again, we have either a KR with red edges or a KB minus 1 with blue edges. Perfect. If you have a KR with red edges, then we are clearly done. And if you have a KB minus 1 with blue edges, we can again add V. By the previous reasoning, we have a KB with blue edges. And so this completes the proof that R of R comma B exists. Are there any questions with the proof? Is there any questions you can ask?
Can you explain the last part? Just the last part.
Like when it has R of R comma B. Sorry,
Yeah.
repeat. Okay, yeah, I'll do that. So if V has at least, did you got that V has the claim that we proved? Here.
Yeah.
Okay, so if we have the first case, that is V has at least R of R, R minus 1 comma B red edges, then all these edges are red. Like this is called the set A, where V has this R of R minus 1 comma B red edges. And so for all x in A, edge V2x is red. Is this clear?
Yeah. Okay. Yeah. Okay. Fine.
So just because we know that R of R minus 1 comma B exists, and the way that we defined R of R minus 1 comma B, that is in this set A, we have
Yeah.
either a KR minus 1 with red edges or a KB with blue edges. So if you have a KB with blue edges, that's what we wanted. And if you have a KR minus 1 with red edges, we'll add V to it. And just because we have that all edges V2x is red, so V is red to these all R minus 1 vertices. And we have a KR with red edges.
Okay. Yeah.
We got it. The other case is exactly similar. Any other questions? Okay. Now we only prove that R of R comma B exists. We don't have any idea about the size of R of R comma B. So is there any such bound? Well, yes, there is. So we have that R of R comma B is at most R plus B minus 2, choose R minus 1. And so how do we go about proving this? Any ideas?
Is this also by induction?
Yes, we will induct on R plus B, but like we have no bound on R of R comma B. So how do we prove this? Yes, the idea is right. Like we induct on R plus B. So we can take the base case 5 or 6, doesn't matter. We take it 6, so we prove that R of 3 comma 3, 6, which is at most 3 plus 3 minus 2, choose 3 minus 1, which is also 6. And R of 4 comma 2 is 4, which is at most 4 plus 2 minus 2, choose 2 minus 1, which is 4. And R of R comma 2, the only value which we precisely know, which is R. This is at most R plus 2 minus 2, choose 2 minus 1, which is equal to R choose
It's equal
1,
to
which is yes. So we have that R of R comma 2 is like this inequality is true for if any when is 2. So how do we do it general? That is, we assume that like we're inducting. So we assume R of R minus 1 comma B is at most R plus B minus 3, choose R minus 2, and R of R comma B minus 1 is at most R plus B minus 3, choose R minus 1. So how does this relate to R of R comma B? Any ideas?
like we are taking like we claim that let's say the right value is x and this one is y. X plus y
Mhm.
minus 1 and this would work.
That's what we did above.
Okay.
Yeah, here. Really. Yep. So this inequality is quite important. So exactly, we'll just use this. That was your proof, right? Like if this is different.
Yeah, yeah.
So we prove that R of R comma B is at most x plus y, just because we showed that x plus y vertices suffice, and thus this is equal to R plus B minus 3, choose R minus 2, plus R plus B minus 3, choose R minus 1, and this is equal to R plus B minus 2, choose R minus 1 due to Pascal's. Oh, I can actually explain. Yes, I think Pablo Sebran has the source of this. Like this proof is probably in Pablo Sebran. We can ask which part you need to go through again. Yeah, recording will also be uploaded. You can ask like which part you want to. I'll just do it. Okay, if there are any questions like you can ask. Oh, So perfect. And also that instead of restricting us to just two values like r of r comma b, we can generalize to any number of values. That is, there exists a minimal number. Okay, just a sec, I'll just write it again. Minimal number r of n1, n2, and so on till nl, such that if capital N is at least r of n1 to nl, and we color the edges of a kn with colors with colors from 1 to L, then there exists an I, there exists I such that there is a kni with all edges colored I. Edges colored I, colored.
How many colors are given?
We're taking L colors.
Oh, I will
Like
not-
we are coloring with colors 1 to L.
Thanks.
So just we were just doing the case for L equal to 2 before. We were coloring with colors red or blue or color 1 and 2. So like exactly same theorem, just generalized. And
Should
again,
we induct on L?
sorry.
Should we induct on L?
Yes, we will induct on L, but we will induct on one more thing. Like for the previous proof, we also inducted on R plus B, remember.
Yes.
So yeah. Yes, we will induct on N. L. Induct on L first. We've done it for L equal to 2. So base case is done. We assume that all numbers L minus 1 multicolor numbers exist. So again, as previously, our step is to remove the bad things too, annoying cases.
Can you tell what's written before edges? I'm not able to get it.
So we're coloring all the
KNI with
edges.
after KNI with what is after that?
Oh, all bad
Oh,
handwriting.
okay.
I'll write it
Okay.
again. So we are coloring the edges of a kn from colors 1 to L, and there exists an I such that a kni has all its edges colored I. There is an I where I is between 1 to L. I is between 1 to L, such that there exists a kni with all edges colored I. Is it clear now? Any questions?
Yes, it is clear now.
Sorry.
Yes, it is clear now. You can
Okay,
continue.
thanks.
Okay.
Yeah. Oh, online math club left the meeting. Like, who is the host now?
It's a bit, but his mic is not working too.
But he just left, right? Like
The
online math club
recording is
left.
going on. The recording is going.
Okay. I thought it stopped. Never mind. So yeah. So yeah, we first proved that R of 2 comma n2 comma so on till nl is R of n2 to nl to just get rid of whenever we have 2, the annoying case. So how do we prove this?
Can you tell what's written before N2 on the left hand side?
Oh wait, I'll just write this again.
And no, why did you write it on this that video?
Oh, doesn't matter. I'll just write it in better writing.
Oh, okay.
R is that minimum number, right?
Sorry?
R is the minimum number, right? That a kn2 or a kn type thing will happen.
Yeah, here is R. Like we just defined it for multicolor numbers. Like instead of 2, we generalize it to L.
Okay, so for this, like if any two edges, let's say the two thing has color red. So if any edge is of red color, there will be a k2.
Yes, perfect.
So there is no red edge, so we can just ignore this two.
Yes, exactly. So is the proof clear for everyone?
Yes.
Perfect. Yeah, I'll just this is super nothing. Stupid things. So perfect. And just because we were inducting on L, we know that this number exists. And now we induct on, like previously we inducted on R plus P. So now we are inducting on N1 plus N1 plus N2 and so on till NL. So we assume that R of N1 minus 1, N2 and so on till NL, and R of N1, N2, N1 and N2 minus 1 and so on till NL, and all these numbers are of N1, N2, NL minus 1. All these numbers exist just because they have a sum which is less than N1 plus N2 plus NL and so on till NL. Just for convenience, I'll call this number S1, this number S2, this number SL. Like wherever we have a minus 1, I'll call that SI for convenience. So like previously, we show that S1 plus S2 and so on till SL minus K plus 2 vertices suffice. Sorry, why am I writing a K? This should be L. Vertices suffice. So yeah, how do we prove this? We have vertex V. It has sigma SI. Sigma SI is just sum of all the si's. I'll just shorthand. Minus L plus 1. So again, as before, we claim that there exists I such that V has at least SI edges. Oh my god, this is edges. What have I written? Edges colored I. Exactly as above what we wanted. So the proof of this claim, if not, then V has at most SI minus 1 for all I. V has at most SI minus 1 edges colored I. And thus again as before, total edges of V is at most sigma SI minus L. So like total edges of V is sigma SI minus L plus 1. So the total edges of V is sigma SI minus L plus 1. But this inequality is a contradiction. So is the proof of the claim clear? Any questions with the proof of the claim?
Can you repeat again? Hold on, take
Yeah,
a
sure.
second.
Yeah, it's okay. So first we assume that all these numbers r of n1 minus 1 comma n2 and so on till nl exists, and r of n1 comma n2 minus 1 and so on till nl exists. So you're getting the pattern. So we call the first number to be s1, like a general number what you wanting to exist is something like this: n1 so on till ni minus 1 and so on till nl. This is calling it si, and we are assuming that this exists.
Uh, I was asking for the proof of the claim.
Okay, perfect. So you got that we have sigma si minus l plus 1 edges, right?
Yes, yes.
So the claim is that there exists in I, this is the claim, there exists in I such that V has at least SI edges colored I. That is for the previous thing we were either wanting at least R of R comma R minus 1 comma B red edges, or at least R of R comma B minus 1 blue edges. So we just, so like this, I can write it as V has at least S1 edges colored 1. This is equivalent to this edges colored 1, or V has at least S2 edges colored 2, and so on till V has at least, or SL edges colored L. Okay, statement of the claim clear?
Yes.
So if the claim is not true, then we must have Si minus 1. We must have at most Si minus 1 edges colored I. This statement. Just because we are assuming that no, there is no such I such that V has at least Si edges. And thus, for all I, we must have at most Si minus 1 edges colored I. Is this statement clear?
Yes.
So now as any edge of V can be either colored 1, 2 till L. So we just sum all these inequalities. That is, the total edges of V would be at most the sum of all these values,
Yes.
which is equal to sigma Si minus L.
Yes.
But the
Then we
total
get
edges of V
the
is,
yes, yes, yes. I got it.
now you got it. So as did everybody get it? Assuming everybody got it. So we have that there is an I, that there exists I such that V has at least Si edges colored I. So we have V right here and Si edges which are colored. All these edges are just I. Perfect. And this number is R of n1 and so on till ni minus 1 nl. So there, so in this there exists either uh, a kni minus 1 with all its edges colored I, or there exists a j is between 1 and L, and j is not I, and there exists a knj with all its edges colored j. So just because the way we defined R of n1 comma so until nl, so we would either have a kni minus 1 with all edges colored I corresponding to this thing, or there is a j such that we have a k and j with all its edges colored j. So if we have this, that is, we have a j which is all its k and j with all its edges colored j, then we are done because that's what we wanted. And if you have the above part, then again as previously we add v. It's because all this set is all its edges I, colored I with V. And this completes our proof. So are there any questions? No questions with this proof? Everyone's, yeah, go on.
No, I just said no, it's fine.
Okay. So perfect. Now all this time that we've been doing, we've just coloring an edges of a KN. We're coloring edges of a KN. Can we do something different? Like instead of coloring edges, can we color triangles? Would the same theorem hold? Well, yes, it does. That the theorem is that there exists a minimal number R3 of R comma B such that if capital N is at least R3 of R comma B and we color the triangles of a KN red or blue, then there exists a KR with red triangles. Oh wait, I want to write this with red triangles. So like these are triangles, just because I'm very lazy. Or a KB with blue triangles. Again, we're not coloring edges anymore, we're coloring triangles. So there exists a minimal number R3 of R comma B such that if capital N is at least R3 of R comma B and we color the triangles of a KN red or blue, then there is a KR with red triangles or a KB with blue triangles. Is the statement clear? Are there any questions with the statement? And so how do we go about proving this? And also we have to assume that R and B are at least 3. Because a K2 or a K1 with triangles makes no sense. So for some initial values, like for example, what is R of 4 comma 3? Sorry, R3 of 4 comma 3. So what could R of 4, R3 of 4 comma 3 be? Any ideas? Hmm. So is this statement clear? Yes, it is 4. Why is it 4? Like how did you just guess it's 4? There must be a proof. Yes, perfect. So if it's 4, then either there exists a blue triangle, or in this case we are done because a K3 is just a triangle, or all triangles are red. And if you have three vertices, you can just color the only triangle red. 1, 2, 3. We color the triangle 1, 2, 3 red. So perfect. So for inducting on R plus B, we've done the base case. Where R plus B is 7. So base case where R plus B is 7, we've done that. And also by this same thing, like the same method that is above, we can prove that R of R3 of R comma 3 is also R. Just by the exact same method. That is, if there exists a blue triangle.
Can you induct on something?
Yes, we are inducting on R plus B.
No, like I mean, Rn of R, comma n will be always R.
Yes, we will do that. Like this 3 can also be generalized. We'll come at the end. First, we'll just do the case of 3.
Okay, okay.
That can also be generalized. Yes. So if there is a blue triangle, then we are done just because a K3 is just a triangle. So otherwise, if all triangles are red, then again we're done. And for R minus 1 vertices, we color all triangles red. All triangles red. Perfect. So like previously, we showed that R of R minus 1 comma B plus R of R comma B minus 1 vertices suffice. Can we do something like this? Like now we can assume that R3 of R minus 1 comma B and R3 of R comma B minus 1 exist. Just because both of these numbers are at least 3 and they sum to R plus B minus 1 and we are inducting on R plus B. So can we do something as before that we show that some number of vertices suffice?
Maybe we will have somehow what is similar proof for R2 and R3.
Yes, there is somewhat similar, but it's slightly different. Can you guess
It
it?
has to be different because
So like last time we did R of R minus 1 comma B plus R of R comma B minus 1. Can we do something similar right here? Any ideas? So like last time we had a vertex V and we had a set A such that all edges from V to A is red. So if we can get that something like A, that for all X and Y in A, we have the triangle VXY is red. Can we force such an A? Or like corresponding B, it's similar. Like, can we force such an A such that all triangles VXY is red?
maybe it forces somehow the same contradiction.
Can you explain more what you mean?
Actually, I'm unable to explain what I mean to myself only.
So we need some kind of an A such that this exists. Like we're not sure that an A exists like this, like set S set A exists. We want N set A. And then we can take this set size of A to be R3 of R minus 1 comma B. And then we can conclude like previously. I'll explain it in a bit more detail if you're not getting it. But if you've got it, can we force such an A? Again, we're just fixing V. So any triangle VXY is just determined by XY. By XY. So if we have a fixed V, so any triangle VXY is just determined by XY. And 3 vertices were determining a triangle. 2 vertices determining an edge. Does this ring a bell? No ideas. Okay, never mind. We'll just formally prove it. So now we show that R of R3 of R minus 1 comma B comma R3 of R comma B minus 1 plus 1 vertices suffice. Where the first R is a previous R we are cutting edges. And this is our R3 in which we are cutting triangles. Again, this is not our R3 in which we are cutting triangles, this is the R we are cutting edges. And this is the R3 now which we are trying to prove. So we show that this large amount of vertices suffice. So as always, we take a vertex V and just call the first number alpha and the second number beta. V has R of alpha comma beta edges. Again, these edges are not going to be colored. Like these are just edges because edges are defined in the graph. We're cutting triangles now. So again, as what I said before, that a triangle VXY and first, this is our graph G, which has R of alpha comma beta plus 1 vertices and is complete, and we're cutting triangles in our G. So any triangle VXY is just determined by edge VXY, sorry, edge XY.
Actually, the approach is more graph theoretic in this system. Actually, I just read the second chapter in Convex, and I have saw that it was a bit less graph theoretic.
Yeah, this is different in Pablo. This is not in Pablo Sebron.
Yes, yes, yes. I just
This is
remember
like
now. I
this is
was
not
just
in
like
Pablo Sebron.
thinking, was this proof in the book? But now I thought no.
No, this is not in Pablo Sebron. Pablo Sebron is like we is just calling basic, not the triangle one. It's just edge one. I just remember.
Yes, I was talking about this.
Yeah.
But that also put the Erdos-Szekeres theorem in a different way.
Oh, they're different. That Erdos-Szekeres and the
Yes.
Erdos-Szekeres proved in Pablo Sebron are different. They're both different theorems.
The statement was way different than yours.
Yes, yes. That was like AB plus 1 numbers, and you have A plus 1 are increasing and B plus 1 are
Yes, A
decreasing.
plus 1 decreasing subsequence of B plus 1 increasing.
They're different. Don't be confused. They're
Yes,
very
okay,
different.
okay.
So yeah, back to where you were. That is a triangle VXY is just determined by edge XY. That is from where this first R comes from. So now we construct another graph H. So H is a complete graph complete graph with R of alpha comma beta vertices. And for all x1 in H, that is x1 is a vertex in H, this corresponds to x in G. G were original graph in which you are coloring triangles, and x is not V. So every vertex in our new graph which you're trying to construct H correspond to some vertex x in G, and that vertex is not our vertex V, which we are like our main vertex. Now in H we will be coloring edges. We're not coloring triangles in H, we're coloring edges. So we color the edge x1 y1 red in H. We're coloring the edge x1 y1 red if and only if the triangle vxy is red. And this triangle is red in G, and we're coloring the edge x1 y1 is red. And x is the corresponding vertex of x1 in G, and y is the corresponding vertex of y1 in G. Is the construction of H clear? Is there any questions with the construction of H? No questions? Like, if there are any questions I can just answer, you can just ask. Okay, assuming there are no questions. And again, we are coloring edges in H, not triangles. And in G, we are coloring triangles, not edges. So now just because H has R of alpha comma beta vertices, we have that H contains either a K alpha with red edges. Again, we're coloring edges in H because H has R of alpha comma beta vertices. Or either a K beta with blue edges. So if H has a K alpha with red edges, so let A be the set of vertices, corresponding oh my god, divided corresponding to these alpha
Will
vertices.
we try some problems also in this session?
Filter which problem?
Uh, we will also try some problems in this session.
Sadly no. I
Okay.
can give you, if you want a problem, probably have one.
No, no, I will find it.
Okay. So A is the set of vertices corresponding to these alpha vertices. A is in G. And these alpha vertices were in H. So we have V and we have A, which is size alpha. And just because for all x1 and y1 in H in the K alpha, we had that the edge x1 y1 is red. Like for all x1 y1 in the K alpha that we had that exists, we have that edge x1 y1 is red. And just because of a construction of H, we have that for all x and y in A, the triangle VXY is red. Is this clear? And as A had size alpha, which we defined it to be R3 of R minus 1 comma B, and thus A has either a K R minus 1 with red triangles or a KB with blue triangles. So if it has a KB with blue triangles, we are done. If it has a KR minus 1 with red triangles, we can add V. And just because of our previous reasoning, like the one we did previous before, and this statement, we have a KR with red triangles. Is this proof clear? Are there any questions with this proof? Like if H has these beta vertices with which are blue, then that is exactly the same. I won't do it. That is literally exactly the same. So is this proof clear? Are there any questions with this proof? No questions? Everyone comfortable with this? Is there any questions you can ask? And also that somebody was saying that this 3 can be generalized to any number S. Yes, that can be done. That is, we can generalize this to any number S. And in that case, we would be coloring a KS. Like a K3 is just a triangle, that's why we're coloring triangles. In that case, we would be coloring a KS. And also these two numbers can be generalized to. Oops. Sorry. What have I written? Yep, perfect. And these two numbers can also be generalized to any number of numbers. Like before, I won't do the proof, it's similar. So any questions with this? No questions? Everyone comfortable with this? Perfect. So now what we wanted to prove in the beginning of the lecture class. I said that we would be proving this theorem. It is it. Maybe. Yeah. So the Erdos-Szekeres theorem which we wanted to prove. That is, there is a minimal number ES of n such that if there are capital N greater than or equal to ES of n points in the plane, no 3 collinear, then there exists n points which form a convex n-gon. So is the statement clear? Okay. So to prove this, we show that R3 of n comma n points suffice. So we label the points. Label the points from 1 to so until R3 of n comma n. Now we construct a graph G. Oh, hello. I'm audible, right? Perfect. So we construct a graph G. This is a complete graph. Complete graph with R3 of n comma n vertices. And we color the triangle of G in this line. So the triangle IJK is red. I is less than J is less than K. If and only if the path the path from point I is the point labeled I, not the vertex I. This is the points that we were labeling, and IJK is the vertices of our graph. So the path from point I to point J to point K and back to point I is clockwise. So again, the triangle IJK were the vertices in a constructed graph G, and the path from point I is the point that we labeled I. These are both different things. So the path from the smallest number to the middle number to the largest number and back to the smallest number is clockwise. Then we color our triangle IJK in red in G. And if the path is anti-clockwise, we color the triangle blue. An example is, let's say we have 1 and 3 and 2. Then the path from the smallest number to the middle number to the largest number, and back to the smallest number is anti-clockwise. And hence this triangle is blue in G. And for another case, we just say 5, 9, 11. The path from the smallest number to the middle number to the largest number, and largest number back to the smallest number is clockwise. And hence this is red in G. Is the construction of G clear? Are there any questions with the construction of G?
No.
Okay, perfect. So just because we prove that R3 of n comma n exists and G has R3 of n comma n vertices, and thus G has either a Kn with red triangles or has either a Kn with blue triangles. Just because we prove that R3 of n comma n exists and G has R3 of n comma n vertices. So both of the cases are exactly the same. So we'll just do the first case when G has at least n vertices, like a Kn with red triangles. So now we claim that the points corresponding to these endpoints, the n vertices, points corresponding, let's write it again because it's terrible. Corresponding to these n vertices is are convex. So the endpoints which correspond to these n vertices are convex. That's what we claim. So to prove this, assume not. Like if not, then just because these points are not convex, then we must have some 4 points such that one point inside the triangle determined by the other three. Just because we're assuming the points are not convex, I'm not saying for every 4 point this must hold. Like some 4 points there would exist that a point is inside the triangle determined by the other three. Okay, perfect. So these the label of these points be A, B, C, and D. And just because these triangles, like the vertices corresponding to these points belong to a KN where all triangles were red. And thus in all these 4 triangles, the path from the smallest number to the middle number to the largest number, and largest number back to the smallest number is clockwise. So we can W log assume that assume A is less than B is less than C. Just because the path from the smallest number to the middle number and back to the smallest number, sorry, the path from the smallest number to the middle number to the largest number and back to the smallest number is clockwise. Then the triangle should be red. And as all triangles are red, we must have the paths clockwise. So we assume that A is less than B is less than C. Now consider the triangle ADB. The path from the smallest number to the middle number to the largest number back to the smallest number must be clockwise. So we have only two cases. That is the first case, A is less than B. Wait, we'll take the first case to be, which is easier. D is less than A is less than B. And your second case to be A is less than B is less than D. Just because in this case the path from the smallest number to the middle number to the largest number, and back to the smallest number is clockwise. And so as it is in the other case, you can check it. Perfect. So in the first case, we have that D is less than A is less than B, and we also know that B is less than C. So we have that D is less than A is less than B is less than C. Now notice the points D, A, and C. And look at this path. The path from the smallest number to the middle number, path from the middle number to the largest number, and back to the smallest number. This is anti-clockwise. But it must be clockwise because these triangles were red in G. And thus this is a contradiction. And so we must be left with the other case only. So in the other case, we have two other subcases depending on the position of C. That is A is less than B is less than C is less than D. Or A is less than B is less than D is less than C. So in this case, again the points A, C, and D give us an issue. That is the path from middle number to the smallest number to the middle number to the largest number, and largest number back to the smallest number is anticlockwise. A contradiction. And thus the only case that we may possibly be remaining is the last one. But in this case, the path from B, consider the vertices B, D, and C. The path from B to D, the smallest number to the middle number to the largest number, and the largest number back to the smallest number, is again anticlockwise, which is again a contradiction. So in any case, we have a contradiction, which contradicts our assumption that these points were not convex. And hence these points are convex, which completes our proof. So are there any questions with the proof? Any questions with the proof I can answer, like just ask. Don't be afraid. Perfect, and that's it from my side. I hope you enjoyed. Like, I was really surprised when I read this proof. A convex point oscillating with Ramsey numbers. So, hope you enjoyed. That's it from
Yeah.
my side.
Can I say some thank you?
Yes, yes, yes.